Cowboy Joe here with a recapitulation of 13.10 on properties of fluids. Your goal by the end of this module will be to describe how fluids create pressure and calculate the. Imagine a glass filled with water. Coming out of the jug, it takes the shape of the jug, but when you pour it into a glass, it takes the shape of the glass. Well, gases do the same thing, and we say these two states of matter flow and call them fluids, which are the states of matter that have no definite shape of their own. Now, if you take those two that we talked about, the liquids and the gases, and you put them in an enclosed container, the molecules will be bouncing off each other and bouncing off of the container. Imagine gas inside a jar. The one molecule maybe will hit, it has a certain speed, has a certain momentum, hit the side of the container and change its direction. Well, that change in direction indicates a change in momentum. That change in momentum is the same as or equal to the impulse. And that impulse is where pressure comes from, that force divided by the contact area, which is what our definition of pressure is. Force on a surface divided by the contact area. Now, force is measured in newtons, the area is measured in meters squared. So our SI unit for pressure would be pascals with the symbol PA. A lot of interesting pressures in this universe. The sun has an internal pressure of 3 times 10 to the 16th. The best vacuum is 1 times 10 to the negative 13. But the most important one on this table is going to be the 101325 number. This is called standard atmospheric pressure. This is a 10 to the 5th. You can't see behind the video recording spot. But if we take the decimal over 5 digits, it's going to be 101,325 pascals. That is the pressure underneath the desk. That is the pressure in the room, air pressure. That is the pressure in the refrigerator. This is standard atmospheric pressure. So let's do 5 problems dealing with pressure. The pressure has a formula of force divided by area. And this one says there's a certain amount of pressure at sea level, and it's about 100,000 pascals in this problem, 2 sig figs on that number. What is the force on the top of a desk that has this dimension? Well, first of all, we know that this Pascal number goes in for the P, and this desk has a rectangular shape to it. If it does, we're assuming it does, then all you got to do is multiply these two dimensions together to get the area. But the problem is we want it in meters. So we have to take those two and convert them first. So 1.52 times 0.76 to get the area. So, and then you can see all you got to do is cross multiply to get the force on the top of the desk. 120,000 newtons of force is on top of the desk. Look at this. This picture is the picture of a spaceship landing on the moon. And you see the bottom of the spaceship has a big flat foot. Why do you think they do that? Well, this is the formula. This moon can only withstand a certain amount of pressure. And if this spaceship has a standard weight that can't be manipulated, lands on the moon, it could puncture it if the area is too small. So by increasing this area, we actually will manipulate or spread out the pressure from the spaceship. You'll notice if you look at the desks and chairs and tables, they do the same thing. So here's your second problem of 5. A child weighs 364 newtons, sits on a 3-legged stool that weighs 41, and the bottom of the stool's legs make contact with the ground over a certain amount of area. This needs to be converted to meters squared. The question is, what is the average pressure that the child and stool exert on the ground? So again, we're asking for pressure. We take the force. Well, the force in this problem is the combined weight of the person and what he's sitting on the stool. So we put those two together, that's going to be the weight or the force on the numerator or in the numerator. The area, we got to change this into meters squared. So 19.3, we can do a little conversion. We know in 1 meter there's 100 centimeters. So if you square the top and bottom, you'll get 1 meter squared is 100 centimeters squared. So we have to square 100, which is 4 zeros. So we have to divide this by a 1 with 4 zeros or move it over normally 2 if it's just centimeters, but not centimeters squared. We got to move it over 4, which is 0.00193. So basically, centimeters squared, you divide it by 100 twice. So that will be our area. And now all we have to do is divide the two. 405 divided by that area to get our pascals. And a lot of times a pascal is kind of small, so they use kilopascals to represent pressure. So either way, in middle, you want to answer in pascals, though. But what if this person was leaning on 2 out of the 3 legs of the stool? If they tilted their stool and was only leaning on 2, how would the problem change? Well, it's still the same weight on the top. You'd still have that same weight on the top. The bottom, though, this area on the bottom is the area of all 3. So we have to basically divide that by 3 and then multiply it by 2, or multiply it by 2/3 to get the area of only 2 legs. So changing that bottom number will actually just change our answer to 315,000 pascals or 315 kPas. All right, here's another problem. You got a lead brick laying on its smallest face. It has a density given. What pressure does the brick exert on the ground? So what pressure? We're looking for P again. We need the weight of the brick. Oh, that's just 12 times 9.8. And what's the area of the smallest face? Well, 5 times 10 is the smallest of the 3 numbers of its dimensions. So 5 times 10, watch out for the unit conversions. So on the top again, it's just the weight. We just got to go 12 times 9.8. And this area on the bottom, we want to make sure we're multiplying meters. So it's going to be 0.050 and 0.100. 2 sig figs in our answer for the bottom, and divide those. 12 times 9.8 divided by 0.0050 gives us 24,000 pascals, or again 25 kPa. It's like decay takes away 3 zeros. K means 1,000. Question 4, in a tornado, the pressure can be 15% below normal atmospheric pressure. So imagine everything's atmospheric pressure. Here comes a tornado. Inside the house is still at atmospheric pressure. Outside is 15% less. So suppose a tornado occurred on the outside of a door. What would be the net force exerted on the door, and in what direction would it go? Would it get pushed in, or would it get pulled outward? So let's work the problem first. Our pressure formula, this P really is the pressure difference. And the area, of course, is 1.95 times 0.91. Watch those unit conversions. But this is the pressure difference. If we have 100,000 outside and it drops 15%, we only have 85,000 outside. And we have 100,000 inside, the difference is going to be 15,000. So standard atmospheric pressure at a 15% drop is going to provide the pressure. So it's 0.15 times that standard atmospheric pressure times that area gives you the force. Now this is the force on the door. The door is going to get blown. Inside has more pressure. It's going to get blown outward. All right, last problem here. Pressure equals force divided by area. I got 10 seconds on the top. We have mass times gravity. On the bottom, we have the weight, or we have 4 tires with that area. So answer for this one, 87,000.